I'm Dr. Bertie Meyer, Senior Lecturer at Mining Department of the University of Pretoria. So the background production cycle, various technology applications within the stoping production cycle. Support cleaning and drilling will be investigated to provide a blueprint evaluation model which can evaluate multiple scenarios of current conventional mining practices where different technologies per production activity can be selected with a value proportion of each scenario application for comparison purposes. The stoping production cycle. The technology of the following technologies were investigated: hydro drilling, power packed where the output is 5 bar, water jet cleaning, power pack output is 20 bar, blast on props to eliminate the insulation and removal of temporary support, permanent netting to eliminate the installation and removal of the nets. They also investigated endless haulage for transport. In layouts, some mines are testing the results in reducing the panel length, but with a current daily cycle, blast cycle an hour is saved on the shift cycle times with shorter panels. Current production cycle times applicable to a 32-meter panel, center to center, or 22-meter panel. So traveling in for both on 90 minutes, waiting place procedure 30 minutes, inter-examination 30 minutes, installation of temper support 45 minutes, installation of nets 30 minutes, marking of a face 30 minutes, drilling and installation install profiles 70 minutes, drilling of panel pneumatic 209 minutes or 141 minutes, and dislodging of a blast hole 20 minutes, charging of blast hole 60 minutes, timing of a blast hole 15 minutes, removal of temper support 30 minutes, removal of the nets 20 minutes. So travel out 90 minutes again, so that gives you a total production cycle of 12.8 hours or 11.7 hours, still not within the required legislation. Current production cycle times. The current production cycle times can not be completed in the allocated time. The biggest contributors are the long traveling times to the working places, because most of the shafts exceeds the optimum distance to the working places due to the lack of sinking of new shafts. Due to the lower face time, the miners are adding additional drilling machines, try to drill quicker, and still use air chainsaws, air water pumps, in-stope full-bolt drilling machines. Jackpot pumps leads to longer drilling times of blast holes due to the low compressed air pressure. A peak times around 2, the pressure is only 2.5 bar, which is required by machine is 4.5 bar minimum to operate well, which leads to late shift clearance, incompletion of rounds, shorter rounds, or increased burden spaces between the blast holes. Current production cycles, legal hours 8 hours 20 minutes for 45-hour work week. So you can see with different stopes, different times, all exceeds allowable time by at least an hour, and you can see the shift clear time as well. 18 around about 7 o'clock is supposed to be at 5 o'clock in the afternoons. Suggested panel production cycle is panel pairing. Panel pairing is 1 and 2 panel pairing method, where one crew is mining 2 panels, and the crew comprises both of night shift and morning shift. Additional drilling and cleaning equipment are required to ensure that enough equipped panels are available for the crew. Some platinum mines are blasting twice a day. This is done on bottom pillar platinum mines. It can be done on gold as well, but a third bed panel is suggested, but the blasting only once a day due to the known seismic events after the blast. Drilling, hydro drilling. This is the drilling time, different drilling machines. Pneumatic machine drilling time for 30-meter long panel, 3 hours 28 minutes. Electric electric machine 2 hours 43 minutes, and for hydro machine 2 hours 20 minutes. And you can note as well that the actual number of drills per panel are reduced from 4 to 3 for your hydro drilling. Cleaning, winch and scraper water jet cleaning. You can see the total cleaning conventional to the scraper is 4 hours 456 minutes, and the water jet cleaning is 380 minutes. Blossom props and permanent netting are tested on the mine to replace the temporary support and temporary netting. The cost of both items are higher, but the reason for justification is using the blossom props and the permanent netting is the benefit of safety due to no fall of ground occurs when removing a camlock jack or the nets. The blossom props are not blasted out. The current support is blasted out often, and that needs to be replaced, and that might lead to loss of blast for a day due to the face that is not cleaned. Endless haulages transport capital layout for endless haulages is very high, and this must be considered in the greenfield mine. And suggested new production cycle. Even with a new technology for stoping productions, the stoping production cycle cannot be completed in the allocated time per shift. So you can see for current practice, longest time is 12 hours 8 minutes, and then for shorter panel new technology 10 hours 1 and 0.1 hours, so that's still not within a 9-hour required cycle. So suggested the split breast production cycle. You can see all the activities are within the time slot of less than 9 hours. So and for shorter panels, even shorter, 6 hours, 6.7 hours. Even for long panels, it's longest is 8.8. So that solves the problem of exceeding the required allocated time. Conclusion, the current step cycle is a concern. Only 8.2 meter crew advances per month is achieved. The mines are saved by high commodity prices and high exchange rate at the moment, and that gives the mines a false picture of achievement at the moment due to the lower productivity. The introduction of new technology doesn't have the desired outcomes because the activities in the current stoping cycle is still not completed due to the long traveling times to the working places. Suggested to implement panel pairing to split the stoping activities into drill, blast and sweepings, support and face preparations. This will ensure the stoping cycle time is used optimally and better crew advances will be achieved, which will lead to higher profits. Pairing requires additional labor to operate the swing panel, to sweep and install support and face preparation for the next drilling shift, but the additional crew advance will pay for incremental cost increase that is required for additional operators. Adoption implementation. The management of mine is interested in implementing this work, where it's at the moment mechanized mining with full co. 2 panels can be time blasted, one at the end of day shift and other panel at the end of night shift. Two panels can be blasted simultaneously at around 1700 hours per day. This can be applicable to gold mines to mitigate the risk of seismicity after the blast, but then the crews need a third panel for charging. Some mines are on the split press concept, two panel per crew at the moment, and the platinum mine is on a 2 blasts per day. It is the best financial option, and the 5-day work week where the annual leave for every employee is taken in December. So this is the very much a workers friendly option. Any questions?
Hi, Bertie Meyer. Can I continue?
I can hear you, Jurgens.
Oh, thanks, Titse. Bertie, I just want to check, we always try to use the same recipe. Why don't we start thinking totally out of the box? And if you look at mechanized mining and the way they set up their processes, is that there's a cleaning cycle, there's a blasting cycle, and the like. So the cleaning cycle, the machines will go in, they will clean all of the ends, then the drilling crews will come in and they will drill, and then the blasting crews will come in and they will charge up and they blast. Why can't we have the same thinking in the conventional setup? Where and I know we are so, crew mentality that we just think about crews. If we change this whole thing around and say, well, there's drillers, there's cleaners, there's supporters, and so on. So you only need those people that's going to do the cycle. So if we want to clean 5 panels, there's cleaners going in there, they clean the 5 panels. Then we, at a certain point in time, send in the drillers and they drill all 5 panels. So now we are bound to a crew, a panel, and doing a certain task. The crew will arrive on that panel to find that, listen, the night shift didn't clean. So now the whole cycle is turned upside down. I really think we need to think totally different when we start to think about productivity and not box ourselves in the crew kind of concept. Thank you.
Yeah, I like that question, because that's actually my dream as well. I actually did that exercise about 5 years ago. There's some new mines to implement it, but they thinking of gold mines, there I suggest that we have 3 race lines equipped on a half level. So then exactly what I said, split operation. So that's a very intent on this first that we did now, flipping activity. So it's not down. Don't depend on cleaning, don't depend on the support, etc., and the cleaning. So my idea is there exactly as I say, you have your then you call it 24-hour operation. So the drillers will come in on 3 shifts and they will drill that 12 panels in that race line. And the next race line, the guys will do cleaning. And the next race line, they'll do the charging support and blasting. And that will actually like about that idea as well, that you then, especially cleaning and supporting side, then you don't have people running around while doing cleaning, other workers there as well. Then that's really to reduce the risk as well. So that will work. I like it. We tried it on the mine that I worked previously. So we actually what did there is actually the preparations on day shift, and then the machine operators only went down at 9 o'clock in the morning. So then that actually worked very well. But as I say, the next step is what we suggested, and I will work on it further. Definitely one race line per activity, and that will actually on the work I did previously for my previous employee, that productivity went up to about 75%. So then what's nice about that, then you can reduce the amount of less supervision, etc. So definitely that is the way to go conventional. But the gold mines haven't got that flexibility. A lot of them only do mining, etc. So I think the opportunity lies in the platinum mines for that.
Thank you, Bertie. Just for everyone, we've got still two presentations to follow, and then there will be a Q&A session after the three presentations, which will take the questions at that point. So please just bear with us. We just wanted to follow the process. You see on the program, there's two other presentations coming through, and then we'll ask the questions at the session just following this next two presentations. Thank you. Can we proceed then, Leslie?
I'm Dr. Bertie Meyer, Senior Lecturer at Mining Department of the University of Pretoria. So the background: production cycle, various technology applications within the stoping production cycle. Support, cleaning and drilling will be investigated to provide a blueprint evaluation model which can evaluate multiple scenarios of current conventional mining practices where different technologies per production activity can be selected with a value proportion of each scenario application for comparison purposes. Evaluating the shift cycle optimization scenario. This is topic following were investigated: current shift cycle scenarios, shift duration, work-related fatigue, labor loss, thermal stress, heat, cost analysis, cycle time for each activity in the shift cycle, drilling time, charging time, supporting time, cleaning time, and tramming time. Current shift arrangement: 5-day work week, 11-day fortnight or FULCA. So the following cycles were investigated. So baseline is 11-day fortnight. Scenario 1, blast every second day. Scenario 2, cycle stoping of 11-day fortnight. Scenario 3, panel pairing stoping. That means one crew gets 2 panels, so then activities are split on the 2 panels. So one will be for drilling, and the other one will be, second one will be cleaning and face preparation. Scenario 4, 2 crews, 2 panels, 2 blasts per day. Scenario 5, 4x6 means 4 shifts, 6-hour duration. And then 4x6, 4 crews, 6 hours work duration, FULCA shift cycle. And then scenario 7, 4x4 FULCA shift cycle means 4 crews, from which 3 are working and the 4th one are on the rotation to replace the crew which is on break. So prediction is scenario 1 at currently achieving 7.2 meters, but if you blast every second day, advance can improve to 12 meters. Panel pairing, crew advance per month 18 meters. Two blast cycles 18 meters. Scenario 4 is 18 meters crew advance a month, and then scenario 5 and 6 FULCA operations 21 meters crew advance can be achieved. So just the breakdown of baseline cost measures for drilling. And you can see scenario 2 and 3 are the cheapest drilling cost. Charging cost the same for all the panels. The average blasting cost per panel is 2,599 Rand. Support costs, that includes your stick support, bolt support, resin support, grout packs. So total support cost Rand per ton is around between 20 Rand and 40 Rand per ton. The cleaning cost, the comparison between scraper cleaning and water jet cleaning, taking all the rope and slash block cost in consideration, energy, pumping energy, the water consumption. So cost per ton for water jet cleaning is 30 Rand and for scraper cleaning 13 Rand. Due to high pumping energy and using of your tons for the water to clean a broken rock. So that's if the cost model takes into consideration tons milled, the recovery grade, the cost, financial evaluation, capital cost, discounted cash flow after tax, and then your capital requirements. So for the pairing two panels for one crew requires additional drilling machines that doesn't expect from machine operators to move the machines between the two panels. So that is additional capital costs. So that is also taken into consideration when doing the financial evaluation on all the different scenarios. And the baseline cost measure can be seen at scenario 4 is the best option. That is where you blast two panels blast twice a day with a 5-day work week. Conclusion: the review of existing shift cycles in the stoping mining methods gives an insight into the success and failures of the application of a stoping mining methods. Scenario 4 are the best practical and financial solutions since the resources, mainly compressed air, are split between two shifts instead of one, as well as your ventilation. Blasting of a charged panel can be done after each shift or once a day at a specific time to reduce the required entry time into the stopes. When blasting takes place only once a day, then a third panel for the two crews are required in the stoping to complete the stoping cycle. Scenario 4 also incorporates a 5-day work week since a minimum of 9 hours are required to complete the drilling and blasting activities on one panel and to clean phase operation on the second panel. Scenario 4 also incorporates the idea that annual leave is taken by entire crew during Christmas break, and that eliminates the requirements of additional employees fulfilling posts for employees on leave during the year. The refresher training and annual medical examination is done during the year on a schedule to release the pressure on the training center and medical facility. Focus scenario is not financial sound, and the negative effect on the employees related to fatigue and required additional relief crews make it the scenario in stoping operation not viable due to the high cost of labor on the mines as well. A lot of absentees is also observed in the FOCO mining operation due to fatigue, and sometimes employees are working double shifts to stand in for the absent operator. Splitting of stoping activities over two panels in a shift is suggested. The suggested scenario to improve the current stoping operations in South African narrow reef mines. The screw advance are at around 7 meters a month at the moment, so that can increase to 80 meters a month. That's incurs a massive rise in your profit by increasing the crew advance from 7 to 18 meters a month. With two shifts will reduce the working levels required, and the shelf will be full to capacity to ensure the mining operation is financially sound. Any questions? Thank you.
Again, we will take the questions just after the next presentation. Thank you very much.
I'm glad to have this opportunity to present our research outcome from the work package 4.6 energy utilization. This work has been jointly done by Mandela Mining Precinct, Center of New Energy Systems from University of Pretoria, CSIR, and Enterprises University of Pretoria. My name is Xianming Ye, an associate professor from Center of New Energy Systems, University of Pretoria. To start with, I'd like to introduce the methodology POET energy efficiency framework that we utilized to guide our research work. The word POET refers to performance, operation, equipment, and technology. So this energy efficiency framework is very useful and powerful. Firstly, if we look at the forward loop from technology to performance, it's actually the process we do energy modeling because we gathering information by energy audit, and it can also guide us the process of energy auditing. And then with all these details of energy audit, we can come up with the system baseline, and based on that baseline, based on the system baseline, it can help us to set up targets, install necessary metering devices for performance verification purpose. And then when we look at the backwards loop from performance to technology, this is the process where we do energy optimization, where we actually design and planning about which technology, which equipment, and what is the optimal strategy of operation in the system. And then the entire loop can actually advise about the financial and technical viability of this work. So underneath the guidance of POET, we actually conducted 3 parts of work. Firstly, we conducted a literature review. Based on the review outcomes, we designed the holistic energy efficiency guideline for the mining industry. Lastly, in order to share the knowledge that we studied, we actually organized industrial workshops in the process. Lastly, in this presentation, we also like to advise the way forward after this study. So our review covers 3 major parts. The first part is the alternative energy resources, which includes solar PV, concentrated solar power, solar thermal for process heat, biomass and biogas, and wind power. All the necessary technical details are given in our final report. The second major category is the energy storage systems, which include mechanical, electrostatic, and electromagnetic, electrochemical, chemical, thermal energy storage systems, etc. There's lots of technical details involved, and then we actually have very interesting discussions with our stakeholders during the research process. The next essential category is the energy utilization optimization via EEDSM approach, which refers to energy efficiency and demand-side management. On my left-hand side, so this shows the categories and strategy for energy efficiency for EEDSM. And the figure on my right-hand side, which summarizes the top 10 most energy-intensive processes in the mining sector. So all of the EEDSM strategies has been proposed to these energy systems. The details can be found in our final report. So based on the review, we come up with an energy efficiency guideline. This guideline actually covers 4 major components: energy efficiency specifications, energy optimization and modeling, national energy efficiency policy framework, and also green fund opportunities. So to enable energy optimization, we need energy models. And there are 2 major categories that we set up energy models: the data-driven energy models and also first principle models. So this figure summarizes lots of the data-driven approach to help us to developing data-driven energy models. And then when we have multiple energy models, we also advise based on the model selection criterion because you would like the model to be true, useful, and simple. So lastly, there's a guideline on the energy modeling process because finally we want the model prediction to be closer to our observed output. So that's the fundamental principle for data-driven energy models. The second energy modeling category is the first principle energy models. And then here is the energy modeling procedure. More detailed explanations are available in our final report. So when we have necessary energy models, we can set up energy optimization. So then it helps us to make decision about how we incorporating alternative energy resources, which energy storage system that we can apply, and which energy efficiency and demand side management strategy that you would like to apply to improve your plant-wide energy efficiency. So energy optimization covers the following three major components: the objective function, the decision variable, and also the constraints. Usually to formulate your objective function, you need to understand your preferred financial or technical or a combination of these indicators such that you can have a multi-objective energy optimization. And then the outcome of this energy optimization are actually those decision variables in terms of system component sizing, which refers to technology and the equipment in the POET framework. Your power flow management, which is a best operation strategy, etc. And then in most of the case, the energy optimization formulations are subject to constraints, such as boundary limit and operational constraints. So as I mentioned, this optimization must be formulated based on the support of energy models, such as your energy price model, weather conditions, and also the technical renewable energy system models, etc. So here is a case study of an optimal battery sizing and operation, which propose an expansion of the battery based on existing setup of solar PV. And then this curve gives the charging and discharging strategy, and this peak also advises the size of your solar PV. And then based on your load condition, the tariff, and then the system can advise you how to optimally operate your PV battery and the grid connection. From the energy policy point of view, we also advised the details of carbon tax, Section 12I, 12L, 12B, energy efficiency policies, and also the Renewable Energy Independent Power Producer Program. And more details are given in our final report. So there's also green fund opportunities from the UK. We have discussed, we collaborate, and we try to apply it for this fund. So we can continue try so and then to obtain more green fund. So to share our research outcomes, we organized 2 industry workshops. So in both workshops, we invited the necessary researchers, stakeholders from the mining sectors, and then we had lots of interesting and essential technical discussions in terms of the plant-wide energy efficiency. We received lots of positive feedback and also valuable comments to further improve our work. So in terms of the way forward, we would like to highlight the following focusing areas. We need demonstration and implementation of the renewable power generation and energy storage systems with the green policy and the green fund. We also need new power business models. As you can see, there is a clear trend of energy efficiency transition from the fossil fuel-based energy generation system to renewable-based energy generation system. And then the key successful factor is the industry academic partner. So where we believe the academic need experts plus postgraduate student training, and then we can generate knowledge transfer, human capital development, which can help to address the challenges of energy efficiency. And then we actually proposed to build a demonstration of optimal sizing and operation of solar power generation system, which is shown in this graph. And then we hope to receive your continuous support for this proposal. Thanks, everybody. That's the end of my presentation.
Thank you, everyone. Thank you for joining us today on this three presentations on track 2. I am Martin Pretorius. I'm the program manager for the longevity of current mines, as well as the mechanized mining systems programs within the SAMERI program. I would like to thank the presenters for your sharp and concise presentations. Presenters were Dr. Bertie Meyer, presenting the optimization production cycle, as well as the optimization shift cycles, and Dr. Xianming presenting the achieving efficiencies in energy utilization. Both of these are from the University of Pretoria. I'm going to open the floor for questions and ask the presenters to join me in responding. Unfortunately, Dr. Ye is not present for this session due to
safety point of view. We're actually doing to nice mines. A salute that identifies the drilling time. So there might be some market on optimizing your production cycle as you mentioned. So that is my question to Dr. Meyer, and then my other question is around the energy systems. Now, Martin, I hear that you said that the presenter is not able to join us today, but maybe you as program manager can assist us, or otherwise you can come back to us after the session. And that is how this work that has been done, how can this actually help us in this energy self-generation options that are now being opened up and are being enabled by the government. Thank you, Martin. Those are my two questions.
Thank you. Bertie, would you like to respond first?
Yeah, we actually on the comparison we did on the drilling is actually we compare the pneumatic with the hydraulic machine that they're using. Actually, we did that study before the other one implemented. So what happened, the drilling is faster. So, but it's, for me, what we realize is not the critical activity in our pipeline. But they also did it actually in the certain operation. But they also did they reduced the. That's why I compared the short tunnel with long tunnel, because they drilling that using a drill down short tunnel with 20 meters. So actually, they presented it on ANSWER last week as well, and I actually questioned to them about it. How did they get to 20 meters, etc. Because you still complete the cycle in 8 hours, because the running is not too far from the shop. But as I say, we actually kept on that hydraulic drilling as well. So for me, that's another huge improvement. So that's not the critical part in that cycle. So for me, what we should use is split the activities, but you have to also ask about that. That is definitely the way to go. So you don't have to, somebody don't have to wait for another one.
Thank you, Bertie. I just wanted to add to that is with this help work which we have done, all of the new technology for hydropower as well as for electrohydraulic, like including the EPROC, was included into this process. But the core focus was also to understand the cycle, the production cycle as a whole, and identify all of the constraints which takes up that excess of 8 hours to almost 12-hour cycle. Having that focus and identify the key areas there of concern, like Jurgens also mentioned, we now can be focusing on full optimization of these processes, not just focusing on the drilling, which is part, very, very high focus area under our work package, but also the other sections as well, to really make that better improved impact to the whole of that mining cycle. Then I'll move over to the second question, Sitsa, the energy systems and how can that help us in this energy self-generation as to the announcement by the government lately. I will definitely request Dr. Ye to respond also formally to you. But just as the base of the work which we have done is also to identify all of the alternative sources throughout South Africa, whether it's wind, whether it's solar, all the various options to go alternative energy sourcing was included into this, this literature reviews and background information which we obtained. And we came up with a workable guideline, which we felt that each case will be definitely unique. And we provided a guideline to show the demonstration of how one should go about to put going through the process, identify the critical areas, the real consumption areas which needs to have focus on, and zoom into then solution systems to come up with proper solutions to that effect. If that answers your question, or I can actually ask Dr. Ye to respond further to that.
Thank you very much, Martin. I think that just the timing is then excellent, and I think it is really just the challenge is how do we communicate this this good work out, you know, into the industry so people are aware of it as they think about this this options now in a much more, you know, with much more urgency and clarity from a regulatory point of view. But thank you very much.
Thank you very much. I can take a last question if there's any last question. Okay, I don't see any hands. Thank you for joining us today, and again, thank you for the presenters today, and hopefully we'll see you in the next track, which is presented after the session. Thank you very much.
Thank you, Martin.
Good day, everybody. My name is Michelle Pinault from the Mandela Mining Precinct, and I'm the Program Manager for the Advanced Ore Body Knowledge Program, or otherwise known as AOK, and I will be taking you through the Resource Atlas. So as you can see, there's a lot of collaborators and partners that's been part of this project, and we will be having Richard from Esri taking you guys through a demo, as well as Sarah from UTILISATION taking you guys through the application of the Atlas. Okay, so the Atlas is an outcome of the work that started in 2018 as a result of the SAMURDI strategy. It's a direct reflection of the vision of the SAMURDI, which is to maximize the returns of South African mineral wealth and to ensure the sustainability of the industry. So the gold and PGM Resource Atlas represents data of over 250 gold and PGM mines, as well as 150 gold and PGM projects. And what we've done is we've actually included some of the upside potential that's offered by strike and down dip extensions of known deposits. Through this atlas, we, as the Mandela Mining Precinct, endeavours to promote innovation in sustainable mining strategies, unlock value, and drive economic upliftment of people of South Africa. So what is this atlas about? So we wanted to understand the gold and PGM resource opportunities, and what does it look like in South Africa? If we know what it looks like and then we understand it, we can determine design specifications for innovative new mining approaches and to convert the resources that we have into reserves. It's also to create an independent compilation of the remaining South African gold and PGM resources within South Africa. We also wanted to understand the past gold and PGM mining landscapes, and this is more from a spatial and geographic perspective, and also to identify missed opportunities that's along with the new opportunities. Currently, we're doing a continued updating and maintenance to ensure that the atlas is relevant and accurate. And we're also doing some work, especially with the guys from Samura, is to identify opportunities against the potential design concepts. And as I've mentioned, Sarah will be taking you through that a bit further. We're also doing a model or creating a model at the moment to classify and categorize the atlas according to some criteria. And this is also to understand the grade, the dip, the channel, the width, and the strike length. What we've seen in the past is a lot of mine underground resources has been abandoned or not mined because it's become too expensive or non-economical to extract. But we believe if we can identify alternative technologies, we'll be able to extract it at a safe manner and profitable. So it's important to understand that there's a process that's gone into the resource atlas and on our data collection and into our transformation of information within the atlas. So what we've done is we've actually spatially captured the information from all over, digital, plans, books, and we've actually captured this information into a database. This includes as well some of the infrastructure, the mine boundaries, mined out areas, everything that we could get our hands on. This information has been downloaded or uploaded in the Nextcloud share site. Through this process, we've also conducted QA/QCing and quality checks to ensure that the information that we've actually captured is also verified and validated. We've also included some UCGS information, which includes road surfaces and also other infrastructure and geological plans. This information was then transformed into Esri and then added to our ArcGIS suite, and then that's how our resource atlas has been created. As I've mentioned, the Samura team is currently doing some work on identifying areas that hasn't been mined, and this is known as the white areas. So as I mentioned, I've spoken a bit about how we created the atlas, but what is the atlas actually? So we know it's a collaborative gateway, the minerals resource information aimed at promoting innovation in sustainable mining strategies, unlocking value, and driving economic upliftment of the people of South Africa. So it's a web information platform. We've got various data sources, as I've mentioned before. We've got a range of users, and it's an easy-to-use app, and Richard will be explaining those apps in more detail. As I've mentioned, it's an easy-to-use app, so you can search, you can visualize, you can analyze, you can collaborate, and the intention is for people to collaborate and use it, and then we want people to contribute. What data is in it? It's all global public domain data. We've got local reference data, some historical data, we've got current mining data, and then any other geological information that we were able to obtain. And we know it's important to have this in a spatial configuration because then you can actually understand, you can measure, you can find things, and you can make decisions. So, as I've mentioned, it's a web information platform. How can we access it? Anyone can access it. You don't need special software or training. All you need is internet, and you need to register at the below link. What are the benefits of this atlas? So we know it can actually serve as an exploration target and a generation tool. It's secure data and access. So all the data that's been added to this database is secure. You can use to indicate areas that still contain potential for future investigations, and that's part of the AOK program that we're currently doing. It allows overlapping of different features. For instance, you can overlay your stoping with your faulting, some of your development ends with some of your boreholes. It provides a holistic understanding of how much resources are left in South Africa. So if you look at one of these plans, you can actually see the whole South Africa resource and reserve database. Interested users can easily discover and view data, and it's a map visualization. So you can actually also do it online, or you can actually download one of those maps or plans that you need. It's simple spatial analysis, and it can be performed by yourself. And as well, what's nice about it, you can do it yourself, and there's an easy to help directive as well on the webpage. So it eliminates the need for specialist software or training. You don't need to download any software or don't have to go for extra training. Everything is available online. Collating of data from different sources and putting it into one central database. It allows safeguarding against the loss of old historical and valuable data. It can be used and overlaid with other tools, such as geophysical and survey software. It has encouraged the collection of valuable geological data from paper copies, such as maps and books, that is then digitized and stored in one secure place, such as in the cloud. Centralization and access to important data sets, and then it has also allowed us to identify areas of opportunity where alternative mining techniques and technologies can be developed for optimal, profitable, and safe extraction. And that's actually the work that the Samira guys are doing at the moment. So the question always comes up is, how much will it cost to use it? And the answer is nothing. To access this webpage is free. All you need to do is register. So how to use it, and Richard will take you guys through it. It's important to understand that you guys need to register on the bottom link to be able to have access to it. So in conclusion, the development of the Atlas and Earth's knowledge and understanding of what was mined, what remains underground, and enable miners and researchers to identify prospective ore bodies that shows potential and could be potentially exploited. Thank you very much. And if there's any questions or queries, you're more than welcome to email me on my email address as indicated on the slide. Thank you.
Hi everyone, my name is Richard Kolfoltz from Esri, South Africa, and I have the pleasure of introducing to you the National Resource Atlas, and we're going to focus on the app itself. So we were given a mandate, or we tried to reach some objectives for this, to create something that is accessible for anyone on a simple web browser. It's as easy to use as Google, but at the same time it provides lots of functionality. It's reliable and available to you at any time, and it will grow with the solution and data as it continues into the future. So a lot of objectives we tried to achieve. So how did we go about doing that? We actually went through a user-centered design process where we worked collaboratively with the stakeholders here at the precinct to identify the purpose and the reasoning for the site, identifying who would use it as personas, and mapping out exactly how they wanted to interact with the system. So we ended up with a few representative personas like Francois, Jacob, Brenda, and Sarah, who gave us an idea on how the system should work. We then designed a little bit of the information on the website. We iterated through some wireframes, and ultimately we created the new site that's available today. So let's take a look at it. Here we are, a simple web browser, and we just go to mmp-resourceatlas.org.za, easy to remember, and up it comes. It's a very simple layout, providing just the information that you need. Firstly, what is the purpose of the website? Who is the custodian or owner of the website? And hopefully drawing your attention straight into the search box, just like Google does. There's one other thing that should be standing out though, and it's a bright orange bar along the top. And that is just asking you to understand the terms and conditions of the site before you get involved. So how you can and can't use the data, and who does not own liability on it. So you need to accept and continue, and the banner should disappear for you this and the next time you visit the site. If you're new or haven't been for a while, there is a big button at the top that opens up a help guide. This will give you a fairly in-depth or detailed view of how to use all the various bits of functionality in the system. Now, before you can start using it, you need to register and have a login. So to do that, hit the register button on the top. And you'll need to provide some basic details like your name and some motivation as to why you would want to use the atlas. That is sent to the administration team at the precinct to vet your request, and once approved, you'll get a username and password to log in with. I'm just going to quickly log in with mine now. And it takes me back to the same home page, but you'll see my username up on the right now. So let's just start by searching. Maybe I'm new and I want to find out something about PGM. What do they have for PGM? So let's just search. Give it a second and you get back a whole lot of results relating to the different types of content or items, as we call them. So you'll see things in there like web applications, data layers, story maps, 3D viewers, all kinds of different content that's already available. If you find something like a data layer, you are actually able to add this to your own map or dynamic map, which is something we call self-service. So really the platform is giving you access to data and you can use it in the way that you want. So here you will see some resource information loading for the Bushveld complex, and it's symbolized according to the reef, as you can see in the legend here. But now you're in a self-service, so you can change the way that looks. Clicking on the symbology tab, you can see what options are currently selected and change something as simple as the color scheme used for each of the reefs. But it's not just the reef that you can use to symbolize the data. You can also use other information embedded within it. You can see some on the list here, but I'm going to use something like the proved grade, I think. That's right. Proved grade. So this system does what we call smart mapping. It analyzes that data and it suggests to you some of the best ways to visualize it. So you'll see here it's chosen counts and amounts, which is really a gradient color scheme across those values. You can see it on the legend at the bottom. But again, I can go and change that. I can change things like how the data has been subdivided into those colors. I can change the color scheme and apply it immediately to the map. Very simple and very powerful at the same time. So once I select that, there are a number of other things I can do to that data. I can set the pop-ups, I can add labels, or I can see some more details about that data and its data source. In the map itself, I can change some settings like adding imagery as the base map, maybe zooming into a particular area. And when I've got a product that I'm happy with, there's a number of tools that allow me to share that. I can print it, I can share it to colleagues, or I can save it for use later. Printing simply opens up a new tab, puts the map in it with a legend, and you can send that off to the printer or save as a PDF. So let's head back to the home page. What happens if you don't know what you don't know? So if you don't know what data is on here, follow the arrow, takes you down on the page, and you'll see some of the curated content that we've put up for you. So here's some applications looking at things like PGM and gold, or a story map talking about resources and reserves, or something that focuses on the Welkom gold fields in 3D. But in this example, we'll have a look at the USGS mineral inventory map. Again, a simple web application opens up here. You're still just in a web browser, no software required, no particular skills or training really, and you should see the familiar shape of the Bushveld complex. Here's the legend, and it's set up according to the styles provided by the USGS for their own data. But there's more in here. I can zoom in, let's pick Rustenburg as an example, and you will see more data appear on the legend and the map, like the project lease boundaries, a label describing who owns it, as well as the existing mine workings in red. If you look a little bit closer, you will actually see the outlines of open cast mining areas, and you can click on it to get a little bit of information about that data. First, it selects the geology, and the next one is the actual outline. You can see an estimated area of that mine pit, as well as the source from where the data was digitized. Other than that, there's a few bits and pieces in here. You can search for locations, you can navigate interactively, and you can turn layers on and off. It's a pre-configured, ready-to-use app available on the Atlas. Let's go back home and see what else. We've added a few more tools at the bottom, just to give you a little bit more capabilities. Firstly, there is the Make Your Own Map, or the self-service map you saw before. There's a more advanced version that allows you to perform spatial or geographical analysis and see how things relate to each other. But in this example, we'll have a look at the resources and reserves viewer. What this does is it takes the data you saw before and it automatically summarizes it in the table you'll see at the bottom. The values in that table are the sum of all the values of the features in the current view. What that means is if I zoom into an area, take for example the Pilanesberg, you will see the numbers update according to the features that are in the map. So I can see there the proved tons, the proved grade will all change depending on what I'm viewing. There's more values, I can keep scrolling to the right, I can see probable PGMs, I can see indicated tons, inferred grade, etc. But here I'm looking at, and you'll see in the legend, I'm looking at all of the different reefs, colored in a different color. What happens if I wanted to look at a particular mine site or a particular reef? There's a quick and easy to use filter function where I can choose a particular project, or in this case, a particular category of resources and reserves. We're going to look at proved reserves. So I tick it on, it zooms to all the features again, and you see the numbers update again dynamically. I'll quickly go back to the Pilanesberg, and you can see the numbers are different from what we saw before, as well as the features in the map according to that filter. This is another example of one of those pre-configured apps that you have access to, and it has a few other bits and pieces in it, like a more advanced print function that allows you to choose, for example, the output format, as well as some other advanced settings like the scale, the size of the map, as well as the resolution or DPI of the output. So that's it. At the bottom of this page, you'll see a little bit more information on how to navigate around. You will see some logos and links to some of the contributing organizations and collaborative partners to the site, and this is continually updated. So thanks very much for listening. We hope to see your registration request soon.
Hello, I'm Sarah Payne, and I form part of the Samira UJ team who have been working on the National Resource Atlas together with the Mandela Mining Precinct. Over the last 6 months, our role has been to identify areas where the Resource Atlas data can be used to ultimately determine new mining and extraction opportunities. So why did we embark on this project? It has become evident that the South African mining industry lacks a central comprehensive database of all mineral resource data in a digital format. This has successfully been achieved in other places around the world, such as Australia, Europe, Namibia, and even the DRC. If you look at this global mineral occurrence map, you will notice that a large cluster of known mineral deposits are situated in South Africa. Nowhere else on Earth do you see such a cluster and variety of mineral deposits. This demonstrates to us why it is so imperative for South Africa to have embarked on such an initiative. As mentioned by Michelle, the Mandela Mining Precinct has successfully compiled a centralized dataset of various geological features, as well as a national inventory of the quantity and distribution of the remaining gold and platinum group metal resource and reserve in South Africa. This is the National Resource Atlas. So now that we've defined the atlas, perhaps you are wondering how it can be effectively used. The Samira UJ team put the National Resource Atlas to use by identifying unmined gold and platinum group metal resources that could potentially be mined by modern and alternative mining methods. During this presentation, I will demonstrate how reliable and robust the data in the atlas is, and just how it can be used to identify potential mining opportunities. I have made use of the Central Rand Goldfield and the northern limb of the Bushveld complex as examples. So, the Resource Atlas was divided into 10 areas in order to address the atlas in workable segments. A standard procedure was established to cross-check the required information for each area and to ensure that the data was QA/QC verified. Each area was selected and standard procedures were followed. The first objective was to determine whether all existing data was accurately captured in the database. Thereafter, the CSIR team updated the area by correcting the digitized information or by adding new relevant data, which had been obtained by the Samira team from reliable sources. For the second objective, the UJ Samira team evaluated the newly implemented data by the CSIR team. This provided a first validation check. Shango Solutions then performed a second validation and verification of the newly updated database. Once the information had been QA/QC verified, it was uploaded onto the live atlas to be received by the end user. Here's an example of the digitizing process by the CSIR. Once correctly georeferenced, a structural plan of the Evander Goldfield was then traced and digitized into the National Resource Atlas. After the information had been QA/QC'd, it was uploaded onto the Natural Resource Atlas. The Samira UJ team could then utilize the atlas to identify areas where the data could be enhanced and used to ultimately determine extraction opportunities. This was accomplished, for example, in the Central Rand Goldfield. So as you may be aware, new deposits have previously been found in Wits by not only understanding the complex interplay between sedimentation and structures, but also by re-evaluating old data sets to identify new deposits within known fields. The Central Rand Goldfield is an example of where the extensions of existing gold resources have been identified in old mined-out areas by reinterpreting existing data. As illustrated in the image, by overlaying old assay plans, reef thickness information, and grade plans, the main channels that carried sediments into the basin to form the ore-bearing horizons were delineated, and this assisted in identifying new potential targets. As accomplished in the diagram shown in the previous slide, this task can effectively be performed by using the National Resource Atlas. One is able to overlay as many important geological features as required. For example, faults and dikes can be displayed, as you can see, and these can be overlaid with stopes, as well as their corresponding contours, and so on. This can all be viewed in both 2D and 3D. So many of you may not want to know where new mining and extraction opportunities exist in the Central Rand Goldfield, and the Natural Resource Atlas is able to assist. For example, the atlas illustrates the limited stopes for the secondary reefs, such as the Bird, Kimberley, and Main reefs, as well as the down-dip extensions of the primary stopes seen via the contours. One can deduce that potential likely remains, firstly, in the secondary reefs, which in the past may have been too low grade to mine, and secondly, in the down-dip extensions of the primary reefs. So, to conclude, this project was not intended to be an end in itself. The atlas should be continuously updated with important information, such as boreholes with assay and collar files, reef thickness, secondary reef information, and so on. This information is often not published in shareholder plans and annual reports and should be provided by mining houses and junior companies that were historically active in these areas. New Witwatersrand and Bushveld complex subbasins are known to exist, but have not been investigated from an economic perspective. For example, as a result of lack of mining activity for the Platte Reef, considerably less attention was previously placed on the economic geology of the northern limb compared to that of the eastern and western limbs of the Bushveld complex. Mining companies are recognizing the complexity of the northern limb and the need to increase exploration and the involvement of academic researchers to better understand these areas. The Resource Atlas can assist in this regard. For example, as you can see on the screen, one is able to display the mined-out areas from the Platte Reef, which, as you can see, are limited. Overlain by the contours of the Platte Reef and the reef thickness, this gives an indication of the remaining unmined Platte Reef at depth. The Resource Atlas could also be expanded to other commodities that are important to the country. For example, we have the world's largest fluorspar resource, where most of our deposits have not even been evaluated yet. It should be kept in mind that yes, there is a need to continue working and updating the Natural Resource Atlas in order for it to reach its full potential, but this is not a small task. The work that has been done to date was a collaborative effort between the Mandela Mining Precinct, Samira, UJ, Shango Solutions, Esri, and the CSIR. Without these interdisciplinary groups, this initiative could not have been realized. Thank you for listening.
So we have a time for one or two questions. So Nasli, I think if you want to post the question that was brought to you, then we can see if we can answer it. Okay, so if there's no questions, the next session starts at 10 to 12. I would like to thank everybody for attending, and if there's any questions, you're more than welcome to mail anybody in the team. Yes, thank you very much. Bye.
Good morning, good afternoon, Mr. Mugera.
Good afternoon, Freddie Mugeri, and thank you, Program Director.
Can you please put your presentation in presentation mode for us?
Okay, done.
Thank you. You can start now.
All right. Good afternoon, everyone, and thank you so much for this opportunity to present to this symposium in June 2021. I'm the chairman of MEMSA, which stands for the Mining Equipment Manufacturers of South Africa. And I will be focusing on the topic driving cluster collaborations in R&D. And what I'm going to do, I'm going to deliver my presentation in two parts, and hopefully I will be done in 15 minutes or so. And the first part, I will spend 2 minutes just introducing MEMSA for those who might not be familiar with MEMSA. And then on the second part, I'll dive straight into the collaborations that we've done with the Mandela Mining Precinct, and also shed some light on what's coming ahead. So to start off with, in summary, we've really made a huge amount of progress on the collaborations that we've done with the Mandela Mining Precinct. And there's a huge amount of opportunity that still lies ahead that we still need to realize. In terms of MEMSA, the key members or key partners that we have, and I'm just moving stuff off my screen here, because I'm kind of looking at myself, and that's not helpful. The key partnerships that we have are shown on the screen, and the anchor partner that we have is really the Mandela Mining Precinct. And our vision as MEMSA is to position South African mining capital goods, components and product manufacturers as a cost-effective, innovative and transformative cluster, which is the preferred supplier to local and regional and global markets. So the key point there is we not only focused on the local, but we also make sure that the solutions are exportable and can be used globally. At the bottom of the screen, you'll see some of our members. We currently have between 36 and 38 members, and we want to accelerate that to 100 members within the next 24 months. And some of the key members, as you can see, we've got Bell, ARD, HPE, and a few other large manufacturers of mining equipment in South Africa. We have a very impressive story to tell on the transformation side, where we managed to get to just under 90% in terms of members that have more than 26% or at least 26% Black ownership in their business. And more than 51% or more than half are at greater than 51% Black owned. And 86% can boast that they've got a B level of higher than level 4. And 26% Black owned in line with MC3, so mining charter 3. So some of the things that we can tell you on that front is that all our members are at least 26% owned by South Africans. And the balance sheets are local, and we export to all over the world. And our biggest market currently is Sub-Saharan Africa. Okay. And this slide aligns with what you saw in JJ's presentation a few minutes ago, just before lunch, where he was showing us the TRL levels and how the Mandela Mining Precinct is positioned. What I want to show here is how MEMSA is positioned. And MEMSA, in general, we start taking part on the collaborations around TRL 6, and we progress the technologies to commercialization up to TRL 9. So, and we are constantly watching what is coming out in the academia and other fields of knowledge development in the TRL 1s, 2, and 3. And also, we start engaging in conversations with the technology development sources from TRL 4 up to 6, and really from 6, that's when we start investing and pushing the products all the way to TRL 9. So as we understand it at the moment, there's quite a number of technologies that the Mandela Mining Precinct has pushed to the TRL space 4 to 6, which our members are looking at, and some are already engaging on that. Let me go on to the next slide. Here on this slide, what I want to share is that, first of all, we collaborate in two major ways: in direct collaborations and also indirect collaborations. And then within the indirect collaborations, we really collaborate amongst ourselves as some members, and also with the parties affiliated with the Mandela Mining Precinct. And all of these collaborations in RDI are done under the understanding that IP is global. So we would want to source IP from anywhere around the world, localize it and manufacture locally and create jobs locally. So to start off with some of the examples on the direct collaborations, the first one is the Isidingo Drill Challenge, which our members participated in together with external parties. As you heard from Dick, the Mandela Mining Precinct is a collaborative environment that involves both local and international parties as well, and not just MEMSA members. So in this particular challenge, there were 11 participants, if I recall correctly, and 8 of them were MEMSA members. And the challenge involved developing the latest advancement in drill rigs for deep level mining. And 3 participants came through and are busy testing their products underground, because they've developed the prototypes and those passed. It was Femel, HPE, and Novatech. So that was quite a nice, successful project, which was initiated by the Mandela Mining Precinct. And then the next one was within the SAMEDI programs, RAM Equipment, one of our large mining equipment manufacturers, also participated in the SETCAP program, where they were looking at how operators behave when interacting with new technologies. So that brought in some really good insight as to what exactly happens and how designs could be improved to make sure that operators adapt easily to new technologies that's being offered. The second one was mounting the latest available visual imaging systems onto machines so that the machines continuously scan the environment they're in and help the mine develop digital twins of their own mine, which are always current. And it will also help with development of safety systems that detect people and avoid collisions and things like that. So that's happened. And the third one is mining Tara database, which to me was the most valuable outcome that came out from collaboration on the marketing front. So if you wanted to know what South African manufacturers manufacture, you log onto the Tara database and you will know that what you're seeing there is what is available from local manufacturers. And in a way, it kind of answers the question around the Mining Charter 3 as to where you can actually get equipment. So moving on swiftly to key direct collaborations that are currently in progress. The major one is the coding of mining inputs, which is already partly funded, and we're trying to raise the last bit of funding, and which also involves the standardization of mine procurement databases. In simple terms, we're trying to get to a point where there's a code for everything that goes into the mine that you can scan, and it would tell you valuable information as to the local content and who the suppliers are and things like that. But most importantly, we want to call a spade, a pen, and not by various names. We want it such that when you search the database, you can actually establish real demand or consumption of certain products that go into the mining environment, and therefore be able to build cases around research, around localization, around local manufacture, really, because to build any business case, what you really need is volumes, an estimation of volumes, so you can actually size up the revenue opportunity and therefore the overall business case. So the next one, which is an ongoing thing that's already in progress as well, is the test mine, which is a very challenging project, and I think it's going to be covered later on in this symposium, if it's not already covered. And there, we've already been together with the Mandela Mining Precinct to Canada to learn from the existing test mine, which in my view is the best available in the world. So, and we want to build the next thing. Then the third one, the collision avoidance system. Here we're collaborating with the Minerals Council, the Mine Health and Safety Council, on the Mandela Mining platform to advance collision avoidance systems. Two of our members are part of this program. Then the last one, Rapid Mine Development Challenge, that is in progress at the moment. It's at the initial phases. So the Mandela Mining Precinct has just launched and invited participants to join that challenge. So we're looking forward to see how that plays out, and we're hoping that it's as successful as the drill challenge as well. Moving on swiftly to the indirect parts where we collaborate with the Mandela Mining Precinct on the RDI. Here, again, we've achieved a huge amount of success, and there's more to be done here. On one of our networks and networking and growth sessions that we held at the Mandela Mining Precinct, a company called Varibox presented, and they were looking for partners who could take their product that they had designed from TRL 5, 6, thereabout into commercialization. And 2 of MEMSA members took up the challenge, and the radial CVT gearboxes were built. And out of that collaboration came out other products as well, 2 of which have already been commercialized and are being used by the mines as we speak. So that was hugely successful, and it was only possible because the Mandela Mining Precinct, together with MEMSA, hosted the event, which outside parties who are in the space of product development caught wind of it and wanted to present their products with the aim of finding partners, and that was very successful. And there were a lot of other events that happened, which put MEMSA members in front of various research units at the CSIR, and I'm just minding my time here. There were a lot of other collaborations, and I'm going to try and summarize in the interest of time, which have also happened where members started working, member companies started working with the CSIR, with the various universities in developing technologies. So I know of one member at least that's probably going to launch a product that they are working on with the University of Witwatersrand. Okay. Then battery-powered vehicles. Everybody in MEMSA who's got a vehicle is looking at that already. IP protection was a major one, in that the Department of Science and Innovation held workshops with members and helped the members understand how IP will be handled in a collaborative environment, because that's a very complex topic. When you're developing IP in a collaborative environment, you need to be extremely clear as to who owns what. So it's not a barn fight at the end of the development. Cleaner production from the CSIR, members are engaged in that as well. Exposure to export market opportunities through the South African Capital Equipment Export Council. So that's all happening, and with a big drive to push exports into sub-Saharan Africa and the rest of the world. Collaborations with universities, I've touched on that. On the individual members, you will be seeing some products coming up being launched from those linkages. And then another important part of what we're looking at is the ISO 44000 standard, which helps with some key principles on how to manage collaborative initiative or collaborative business relationships. And this is my last slide. And here I want to just finish off by quoting Kaplan, who said to us, South Africa has a significant cluster of firms in mining equipment and related services, which are at the global technological frontier. And I didn't believe this part until I saw it for myself when I moved around the world and realized that actually our biggest competition is probably Canada and Australia and China, and we're not far off. This is evident in respect of trade, exports, IP, and leading products instead of this cluster. Indeed, this cluster is the only significant area of industrial activity where South Africa is located at the global technological frontier. So we need to really take advantage of what we've got. It's always been strong from the days of Comro. We lost it a little bit, and there was some erosion there. And now we are back to this collaboration to rebuild and grow new capabilities in order to grow our local manufacture, reindustrialize South Africa, and create the very important jobs that we really need we're currently sitting at crazy level of unemployment, and we in this forum can do something about it. Let me end there, Program Director. Collaboration is very alive, and there's more that we know we're going to achieve in collaboration with the Mandela Mining Precinct. Thank you.
Thank you, Mr. Mugeri. Do we have any questions? Hi, Benita, would you like to ask a question?
Hi, no, just acknowledging the presentation and with thanks.
Thank you. Okay, if we don't have any questions, we can move to the next track. Thank you. Thank you, Mr. Mugeri.
You're welcome.
Hello, I'm Elise Stain, and I was part of the CSR team that was responsible for developing a data architecture as part of a real-time information management system for the mining sector. Now, in a mine, a stope is known as the open space that is left behind when desired minerals have been extracted. These stopes can have sensors, meters, or actuators that can take certain environmental measurements or monitor conditions. This may include temperature, dust levels, oxygen, and energy pulse readings. Now, the data obtained from these sensors could be used to assist with mine-related problems or with informed decision-making. However, a quick response to changing conditions or sensor readings can only be conducted if these readings can be accessed from and analyzed on a local on-site computer in the mine. For more computationally expensive analysis and storage purposes, it may also be of great value if these measurements could be transferred to a platform in the cloud. So a main objective of our study was to therefore develop a data pipeline that would allow the flow of data from these sensors in the stope of a mine to other locations where the data can be utilized. We specifically focused on developing the pipeline to allow the flow of data between 3 different locations. First, the data had to flow from a sensor in the mine to a local on-site computer system where the data can be viewed or analyzed by someone in the mine. Furthermore, the data from the sensors had to flow to the cloud where more computationally intensive activities can be done and where data could be stored. Finally, the pipeline had to allow the flow of data from the cloud to these local on-site computers and vice versa. Now, since we didn't have access to actual sensors in the mine when this project commenced, we simulated data to represent readings from such a sensor. This diagram gives a short overview of how we created the pipeline to allow the data to flow from the mine to a local on-site computer and to the cloud. So first, the data had to be compressed to a smaller size before transmitting it and encoded to a language that can be understood by the different components of the pipeline. Since the data was simulated and no wired connections were available, a messaging broker was used to transfer the data from the sensors to an Internet of Things or an IoT gateway. So this gateway serves as the connection point between the sensors in the mine and the local on-site computers or cloud. All the information moving from the sensors goes to this connected gateway. Our pipeline was further expanded by connecting the gateway to a modular integration platform that is used to remotely manage the different devices, or in our case, the sensors that are connected to the gateway. The data was then finally transferred from the modular integration platform to the on-site computer using a streaming platform. On this local on-site computer, a user could now access, visualize, or analyze the sensor data in near real time. In a similar way, the data was sent from the IoT gateway to a data science platform in the cloud. On this data science platform, data visualization and exploration tools were implemented, where various tasks could be performed on the data. For instance, it could be used for analysis purposes, for visualization purposes, or even for training a machine learning model. After developing this data pipeline, the next objective was to develop a machine learning model in the cloud that would use the sensor data from the mine to assist in solving a mine-related problem. This could, for instance, be used to serve as a decision support tool or to provide an early warning system based on near real-time measurements from sensors in the mine. So the purpose of machine learning is to develop a model from historical data of the system under study with the aim of making predictions for that particular system from new, previously unseen data. The first step in developing such a model is to gather a suitable data set on which the machine learning model can be trained. We considered a data set containing seismic bump measurements at a mine in Poland. This data set encapsulates geological conditions in a longwall coal mine to determine whether a mine is subject to rock burst, which could ultimately result in a seismic hazard. So the data set consists of different kinds of readings, including hazard assessment results, energy pulse readings, the number of seismic bumps recorded within a previous shift, and then also a decision attribute, which is in this case listed as class in the sheet. Now, all other readings other than the class attribute describes conditions for a particular, or let's say a current shift, whereas the class attribute describes a condition for the shift following this particular one. For the class attribute, the number 1 indicates a hazardous state, which means that a high energy seismic bump, which is usually more than 1,000 joules of energy, occurred in the following shift, whereas the number 0 refers to a non-hazardous state where no high energy seismic bump occurred in the following shift. So the objective of this part of the study was to develop a machine learning model to determine whether a hazardous state can be expected in the next shift by considering the geological measurements of the current shift as input. Now that we have identified a suitable training set, the next step was to develop a model. For this study, a classification type neural network model was considered. As input, the model would be given the geological conditions of a particular shift, which consists of that shift's energy readings, seismic bumps, pulse readings, etc. The model would then give a classification as an output. So this classification would either be a 0 to indicate the non-hazardous state in the next shift, or the number 1 to indicate that a hazardous state can be expected in the next shift. Now that we've trained our model on the seismic bumps data set, we can now use this trained model in the mine. So the current shift's energy, pulse, seismic bump readings, all of these measurements which the model has never seen up to this point can now be fed to the model, and then the model will predict whether the next shift contains a hazardous or a non-hazardous event. After testing the performance of the model, we found that the trained neural network would generally predict a hazardous or a non-hazardous instance in the next shift with an 86% accuracy. So what does that mean? It means that for every 100 seismic events, the model would accurately classify about 86 of them as hazardous or non-hazardous. Right, so a machine learning model that predicts whether a hazardous seismic event would occur during a following mining shift based on the previous shift's sensor readings has now been developed and trained in the cloud. We then sent this newly trained model to the edge, which basically means that the trained model was now available on the local on-site computer system in the mine. The data from the sensors could now be sent directly to these computers, and the model could, in near real time, predict whether the next shift would consist of a hazardous instance or not. So what would the person sitting behind the computer in the mine see? We visualized our model's output as follows. During each shift, the model would consider the measurements and the readings in the current shift and make a prediction on whether the next shift would contain a hazardous instance or not. If the shift did not contain a hazardous instance, the number 0 would be plotted, or at the 0, it would be plotted. If a hazardous instance was predicted, a 1 would be plotted. On the x-axis, the time of the current shift is given. If the person in the mine therefore sees that a hazardous instance has been predicted for the next shift, that person can look at this table on the left and see what probability did the model give to that instance actually occurring, and then make a decision on what to do next accordingly. So in conclusion, we've developed a data architecture for data to flow from a sensor in a mine to a local on-site computer, as well as to the cloud. We've also developed this architecture to allow the flow of data from the cloud to these local on-site computers and vice versa. And then finally, we've developed a deep learning model in the cloud that would use the sensor data from the mine to assist in solving a mine-related problem, and deploy this model on the local on-site computers in the mine so that predictions on new data can be made in near real time and necessary decisions can be made timelessly. Thank you.
Everyone, welcome to track 11. Sorry, I didn't get a chance to welcome you and introduce the speaker at the beginning, but I'd like to do so with our second lightning talk speaker, and this is Dr. Nikoline Witter. She's a researcher at the CSR, and she'll be talking to us about modeling and visualization in this 4IR in mining track. Thanks, Nasli.
The title of this talk is Modeling and Visualization, and the study was conducted by myself, Kirot Budraj, and Rian van der Doel, also from the CSIR. So the objectives of this study is to demonstrate distributed processing, analytics, and the aggregation of geospatial vector sensor data to implement distributed processing solutions such as Spark and GeoSpark into an existing streaming data infrastructure, or SDI, and finally, visualization of different data types from multiple sources or platforms in a graphical user interface, or GUI. So in order to reach our objectives, suitable input data is necessary. And for this, we simulated 2 data sets, and this was done due to a lack of available appropriate data, and we used Python to do this. In a previous phase, a streaming data infrastructure, or SDI, was put in place. The real-time GPS coordinates and temperature readings of some vehicle moving back and forth between 2 locations are simulated, and this was done to show the implementation of near real-time sensor readings into the SDI. For the next data set that we simulated, the relative position of 5 individuals or workers walking in different directions through a tunnel with a narrowing in the middle was simulated. And this was done to demonstrate the aggregation of different data streams at near real-time streaming analytics. And finally, the last data set was not simulated, but obtained from a different platform, a data science platform, where a geo event or a seismic event was predicted for a mine, and a model was run using machine learning to predict if the event will occur or not. All these data streams and data sets were sent to the streaming data infrastructure using Kafka. So for the streaming analytics part, the relative worker location data consists of 5 data streams that are aggregated before analytics can be conducted. We calculate the relative distance between individual pairs at different times in order to determine the distance between them. If the distance is less than 1.5 meters, then an proximity event is recorded. As you can see in the image here, we compare the different individuals, and then in the first table here, you can see person 1 and person 2 were 0.97 meters apart, which of course is less than 1.5. And so the time of this occurrence, as well as the ID of the individuals and the distance, are recorded and saved. So in order to be able to use this data, it must be saved into some type of database. All raw sensor data is considered Internet of Things, and so saved to a Frost IoT database. At the top, you can see observations and location, which is data from the first GPS and temperature dataset are saved into a Frost database. And below, you can see the analytics and results from the machine learning saved into a Django database. And this is just kept separate because it's different types of data. So finally, the different data sets must be visualized in some type of graphical user interface. We decided on Dash, which is a Python application. So the first data set, GPS and temperature data, is in the first tab here named temperature sensors. So as you can see, the temperature data is recorded in the graph, and the orange or red dot is the current temperature, and it's updating in real time. The corresponding GPS location of the vehicle on which the sensor is mounted is shown in the map next to the graph. Below, the temperature and positional data is aggregated, and the last 10 readings is shown in the table. So next, the worker's relative positional data is shown in the tab named Contact Sensors. So here, the raw sensor data of the relative positions of the workers is shown in the graph, with once again the big dot showing the current location, and the results from the analytics is shown in the table. The graph can be moved back in time to show snapshots at previous instances by using the slider, and the table, which contains the time that the event was recorded, as well as the individuals involved and their relative distance from each other, can be filtered using the controls below. Finally, the prediction results from the data science platform is shown in the third tab. When a geo event is predicted, a 1 indicates that an event will occur, and a 0 indicates that the probability of an event occurring is very low. So in this figure below, you will see there's zeros and ones showing the absence or the presence of a seismic event or that will occur. And in the table next to it is the time that the prediction took place, some parameters used in the prediction, such as maximum energy, and then the probability of the event occurring. So here in this case for event 571, the probability of a hazardous event is 0.59%, or in this 59%. So if we look at this, there's a lot of hazardous events, which is not good for a mine. But this is because even though the data was measured at an actual mine in Poland, it's in a static database and the data is randomized. It's also sped up so that such a prediction will not take place at this frequency, but significantly slower, perhaps once or twice a shift. And all this has now sped up and showing these hazardous events due to just the sped up for demonstrative purposes. In the case where a hazardous event is predicted, the warning light at the top will show red, and if no hazardous or seismic event is predicted, the light will be green. So in conclusion, near real-time and efficient analysis and processing of rapidly streaming data coming in from multiple sources was conducted and implemented in the SDI. Due to the versatility of Dash, it was possible to easily upscale the user interface to incorporate the visualization of different data types, such as near real-time streaming and sensor readings, streaming analytics, and machine learning results. Thank you.
Thank you, Dr. Nikoline Witter. I have the pleasure of announcing our next speaker for the lightning talk entitled Machine Learning for Subsurface Geological and Geophysical Decision Making. And Dr. Glenn Waila is an adjunct professor at the University of Witwatersrand, will be presenting this. Thanks, Nazli.
Ladies and gentlemen, thank you for joining us in this talk. So today I will be taking you on a journey that speaks of machine learning applied to subsurface geological and geophysical decision making. This is quite an important presentation given that we're in an era where data occur in very large volumes and we need to find a way to analyze it. So the purpose of the talk is not to eliminate the fundamental geological and geophysical analysis, but is to provide a tool to aid the analysis. So before we go further, I would like to define something, which is big data, because everyone speaks of big data. I just want to say that the mining and metals industry have been dealing with big data long before the commercial and technology industry started working on big data. And by big data, I mean the following. I'll describe this or summarize this in 5 V's. The first one is that we have large volumes of data, so many samples that we collect, and sometimes it's so difficult to handle and visualize. The second one is mainly the velocity that we tend to find in this data. So it's the high rate of collection that we tend to see, and is continuous as compared to other industries where they collect data once in a while. The other one is more of the variety, where we speak of data coming from different sources. So we'll have data coming from survey department, data coming from mining and geosciences. There's also a high variability of this data, meaning the acquisition changes during the project time and during the mining life cycle. And the last one is the veracity, where the data itself is various levels of accuracy. So some of it comes in qualitative formats, such as many of the geological observations, while some of it comes in quantitative formats, such as the chemical assays that we tend to have, including geophysical data. So, to do this, it means that we are now living in a world where we need a new way of doing things. And as I have mentioned, mining and metals industry has dealt long time ago with big data. The only thing that we have to do is that now there's a growing toolbox of all the new emerging data-driven methodologies. And with this, we need a new approach to deal with geoscience data, which needs to include the following. The first one is going to be the domain expertise. So we still need people who are fully trained as geophysicists and fully trained as geologists. The second one is more on the statistical modeling. The last one is more on the coding. And in between, that's where the solution lies. So for the purpose of this talk, I will use one case study, which is the Bushveld Igneous Complex located here in South Africa. And the main aim is to investigate how big data sets can be used for the prediction of many different attributes, such as geological features. And in this case, I'll use a case study of potholes. So let's look at something here. Firstly, we need to come up with a method of some kind. The most prominent method that is more easily available but difficult to process is mainly seismic data. So the first one is that we need to come up with a method where we apply machine learning to seismic data to automatically identify these potholes. But the journey starts in the beginning, where we do post-processing of the data that was acquired long time ago. And with this, it means we need to extract specific seismic attributes, and seismic attributes can be defined as any measure of seismic data that helps us to visualize or to visually enhance and quantify features for the interpretation of specific features such as potholes. And to do this, we have to develop some sort of a methodology. And here I will quote my colleague Musa Manzi and other colleagues who have worked on this methodology to extract key seismic attributes from older geological data. So the first one is mainly seismic data migration, staking and migration. And this will be followed by more of importing the data into a suitable type of a format. And for this, we can use programs such as MATLAB. And after this stage, we have to go and compute these seismic attributes. So there's two methodologies that have been developed. Much of it have been headed by two of my colleagues, Michael Westgate and Musa Manzi. The first one is conventional based methods. The second one is non-conventional based methods. And both of them have their own advantages and disadvantages, which I will cover in part for this presentation. And after this stage, what we do is we go into the main categories that we need to look into. The first one is mainly tracing these attributes, and by this methodology, what we aim for, it's more effective at characterizing pothole profiles, as you can see in the left diagram. The second one is more of horizon attributes, where it is more effective at characterizing pothole expanse, or including their diameters and shapes in different volumes. Let's look at another one here, where we look again on reprocessing some of this seismic data. So you will notice on the diagrams that are shown in here that there is a time slice horizon that is depicted. And in there, this is where now we start extracting some of these key features that defines the potholes. And this may include things such as the side angles of the potholes, their diameters, and so forth. And all these data sets tend to be quite useful for the prediction spatially of where the potholes may be located and their characteristics. And after this stage, what you see in here, it's a state-of-the-art type of mapping where we have sequentially picked up different potholes using geophysical seismic attributes that we have extracted. And from this data, this prepares our way to do detailed machine learning work. And on the bottom right there, you see a map, which is more of a geophysical model extracted using some enhanced type of algorithms that helps us to notice anomalies in a form of potholes, and that map clearly details that profile. As we move from that, now we have all our data set to start doing some machine learning. So what you're looking at here is a parallel coordinate system. For those who are doing geology and geochemistry, they will notice this as a typical spider diagram, but here it's more enhanced to look at many other things in different dimensions. So what you are looking at here is cluster analysis of different potholes, and you can see we have managed to pick from the seismic attributes up to 5 potholes of different sizes. But what we have to do next is to look at the following. In the left-hand side, you will notice that we can spatially now locate the different sizes of the potholes, but not only the potholes, the linear features such as the faults have been clearly been marked or demarcated. On the right-hand side, what you're looking at is using some of these key seismic attributes such as the diameter of the pothole, the side angle of the pothole, to make predictions of where are we likely to encounter what size of a pothole and what sort of dimension it will be looking like. To summarize what I have just presented in the previous slide, the Bushveld complex has generated enormous amount of data sets which provide us with insights. So the advent of modern seismic processing techniques and computing technologies has enabled us to constantly extract key features such as the key characteristics for the potholes. So with this approach, it means we can plan ahead where to find the next pothole and what sort of dimensions will it be having, and to also characterize what sort of depth, diameter, the side angle, which are key excellent features that can be utilized in machine learning. So we have demonstrated this using agglomerative type of clustering, which is a form of unsupervised machine learning algorithm. And to take this further, we're going to be using these learnings that I have presented here for the next phase of an AOK project 5.7, which looks at statistical learning for the prediction of potholes. Again, I would like to thank everyone for joining us.
Thank you, Dr. Glenn Mwala. Interesting application of data and modeling and machine learning. Our next speaker that I'll introduce to you is Ms. Humna Malik. She's a senior engineer at the CSIR, and she'll be sharing with you a lightning talk on the ARTEMS blueprint, which is the case-wise tools that we have adopted and done much of our work on. So it's over to Humna.
Hi everyone, my name is Hamna Malik and I'll be taking you through the ARTEMS blueprint and specifically the use of case-wise tool. This is all part of the ARTEMS research project. I'm here on behalf of the CSIR and this research is commissioned by the Mandela Mining Precinct. So a quick overview. I'll talk through the scope of ARTEMS and then the ARTEMS integration blueprint. Then I'll go through a scenario with the mine manager having an overview while she sits in her office of what's happening in the mine. And then we'll go through the integration of the ARTEMS blueprint in case-wise. Okay, so ARTEMS had a roadmap of research that had to be addressed. The research done in the various research projects can be used in the different places in the mine. And I'm not going to elaborate on all of the research projects that were done as part of ARTEMS. I'll focus specifically on the ARTEMS integrated design and blueprinting research project. This research project is responsible for the integration of all the other research projects. These research projects need to be integrated in an architecture. So if it's a technology, how will it support the next technology? How will it support the operations that it does? How will it integrate to the people that work there? How does it integrate to the value benefit that the mine needs to achieve? So here we've got a scenario of where the mine manager is sitting in an office or probably even working from home now that we're in the COVID situation. So she has an overview of what's happening in the mine underground. She doesn't need to physically be there, but she can access operational and safety data in real time. Then we've got the shift boss. You can see this the highlighted person underground in the mine. He is responsible for the daily, weekly, and monthly reporting. So he can walk around with a tablet or a smartphone and log information electronically from underground in the mine And all of that information is uploaded onto the system, and the mine manager sitting in her office can access it remotely in real time. Then, due to the rugged and non-line-of-sight operational conditions at the stope phase, the normal line-of-sight ICT solutions like the Wi-Fi don't offer stable and robust solutions for the stope operational requirements. Non-line-of-sight is something that the military soldiers experience when they're underground, and that led to the co-FDM technology that we thought is applicable to the mining environment. This technology gives us the ability to still communicate even in the non-line-of-sight conditions. So this allows us to still have communication even in the last 100 meters, say, for instance, in the drilling site. It doesn't use any equipment that you need to have installed, so you can walk around with the equipment or even hang it anywhere, so it's quite suitable. The real-time communication service at the stope phase will enable more effective mining operations. All stope-related maintenance and operational information could be reported and resolved much faster, as information could be communicated to managers and maintenance personnel in real time. The manager sitting at her office could be making decisions in real time, hence leading to much faster and effective mining operations. So this is a picture of the homepage of the ARTEMS model in case-wise. Let's talk through the enterprise architecture approach, and then we'll come back to this model. So the enterprise architecture describes the business in terms of these 6 domains that you see on the screen. In this case, the mine is an enterprise. To describe an enterprise, there are 6 reference models that we use, which are divided into 2 parts: the business architecture and the solutions architecture. So the performance reference model is about what are the objectives that you're trying to achieve. What's the purpose? That purpose can be indicated in specific performance measures or KPIs. Then we have the organizational reference model. This indicates who you need to have in the organization in order to achieve your goals. Then there's the business reference model, and this indicates what the value chain of the mine is. This includes things like the drilling and blasting and excavation, etc. Then the second part is the solutions architecture. The picture that I showed earlier with all the research projects within ARTEMS, that relates to the services and the technology reference models. And then the information reference model is about how the information flows from underground, perhaps to the control center or even to the mine manager sitting in her office. So this is the architecture that needs to be addressed, and case-wise enables us to do that. It shows that all the things are interrelated and integrated, how technology is linked to a person or linked to the KPIs, etc. By incorporating all of this information into the architecture, we can use this architecture to see where the gaps are or where the technologies are not linked to certain roles or processes or KPIs. Let's do a quick demonstration of the actual case-wise tool. So you'll see the different functions here in the tool, but I'll just focus on 1 or 2. So if you go to the SAMEDI program, here you'll see all the programs that are part of the SAMEDI program, and since we're focusing on ARTEMS, I'll open that link. And now you see all the research projects that are done as part of the research, as part of ARTEMS. And if we click on ARTEMS, then you can see the different phases of the ARTEMS research project. Now let's go back, and I want to show you some of the deliverables that are linked to this case-wise tool. Again, we go to ARTEMS, and these are all the different work packages, and I'll just pick on one of the random work packages. And here you can see all the technologies that are related to this project. Now, if I click on this link here, then you'll see the properties page pops up. Then you just click on that link, and you are able to download that deliverable that was submitted as part of this work package. And you can do that with any of the research projects. All the deliverables are linked in this model. Okay, thank you.
Great, thank you, Hamna. So just to summarize, we exposed you to some of the work that we've done over the last number of years in the ARTEMS program. And you would have noticed that there's a strong emphasis on integration. So it's one thing to have lots of data. It's another thing having various tools and various architectures, but how do we pull it all together? And that has been a strong focus of ARTEMS in integrating all of this. So we looked at the data architecture that was presented by Stein. We looked at the modeling and visualization tools. And the great thing about the demonstrations and the proof of concepts that were done prove that it can be done with a very low cost, at low cost means. The systems and the open source software that were chosen, the platforms, the APIs are readily available, and it does not have to be an expensive exercise. Then Dr. Glenn gave us an insight into how they are doing actual use case in terms of potholes modeling with big data sets and the approach that they've taken in analyzing it and coming up with solutions there as well. And then finally, it was that presented the case-wise tool set to you, which we will be opening up in the near future for all to see. Just an interesting point relating to that is that it consists of just from a research point of view, over 100 reports, technical reports, containing various assessment results, desktop studies, technical specifications, hardware, software, etc. So look out for that. Any questions or comments before we move to our next and final session for the day? Nazli, I don't know if you've received any, but I don't see any in the chat box.
No, I haven't received any questions.
Good. Then I think we can close this session and the next session and move on to the final session for the day. Thank you, everyone.